Good morning. My name is Giacomo Moretti. I am a research fellow at the Intelligent Material Systems Laboratory at Saarland University. Today, I will talk of smart materials called dielectric elastomers and how they can be used to build loudspeakers. The research that I'm presenting is a result of the DTune project. This is a Marie Curie fellowship sponsored by the European Commission, of which I am the beneficiary. DTune investigate loudspeakers in which the vibrating diaphragm and the actuator are combined into a soft, active dielectric elastomer membrane. So in contrast with traditional dynamic loudspeakers, here there is no moving coil, and the sound is generated by the vibrations of a dielectric elastomer membrane driven by Coulomb forces. Dielectric elastomers, DEs, are stretchable dielectrics which can be used to build variable capacitance actuators that deform in response to an applied voltage. Among other dielectric elastomers have been used in the past to develop fluidic drives, soft robots, and wearable devices. Thanks to the ability to work at frequencies as high as kilohertz, in the past, also different layouts and prototypes of dielectric elastomer loudspeakers have been built and presented. We consider a special device layout called cone dielectric elastomer loudspeaker. This is a flat annular membrane covered by electrodes, which is pre-stretched, deformed out of plane, and connected to a biasing element, for example, a spring, through a central disc. When a voltage is applied on the electrodes, the membrane surface expands and makes the central disc move out of plane linearly. This layout is commonly used in the actuators for several applications, and it has been used in the past also as a loudspeaker. Compared to other implementations that I've shown, for example, in the previous slide, this system is simpler and does not require any pneumatic biasing. Now, in our previous works, we have shown that the ability of this system to generate sound, at least in the mid or upper regions of the audible spectrum, does not depend on the pumping out of plane motion of the device. It rather depends on a series of structural modes that characterize the membrane dynamics at high frequency. That is, by blocking the central disc of the device, the speaker still preserves its ability to generate sound as a result of the membrane voltage-driven transversal vibrations. You can hear that in this movie where the cone has its central disc fixed. Recently, we have used this observation to develop multi-mode dielectric elastomer transducers that can concurrently work as linear actuators and loudspeakers. We started from the observation that for certain choices of the design parameters, the frequency ranges where the device produces a linear pumping motion and the ranges where the structural modes are excited are highly uncoupled. Sound is only generated as a result of the structural modes. That is, the sound level generated by the DE is the same both when the central disc is let free to move along the axis or when it is blocked. So exciting the DE with a multi-chromatic voltage with a low frequency, large amplitude component and a high frequency, small amplitude component, one can concurrently obtain a linear actuation and an independent sound output that are produced by exciting different vibrations mode at the same time. Here, just as a proof of concept, you can see the membrane working as a speaker and a metronome that beats the tempo of the tune through its linear motion. Among other, these principles can be used to develop audio-tactile interfaces that can produce co-located, concurrent, vibrotactile and acoustic stimulations, and even detect a user's touch via capacitive sensing. If you are interested, I invite you to have a look at our paper on these on advanced functional materials. We developed a multi-physics model of the E-cone loudspeakers with blocked center using the structure shown here. The model combines an electroelastic model of the DE and a model of the acoustic domain. The DE is described as a hyperelastic dielectric, and the acoustic domain is described by Helmholtz equation. The models are fully coupled, meaning that the membrane dynamics affects the distribution of the acoustic pressure, but also the acoustic pressure produces loads that affect the membrane dynamics. The output of the model is the distribution of the sound pressure around the speaker. We implemented this model via the software COMSOL Multiphysics. We treated the elastomer as a membrane element, and we introduced the effect of electroelastic coupling via custom equations. To consistently couple the membrane model, which is formulated in a Lagrangian fashion, and the acoustic model formulated in a Eulerian fashion, we used moving meshes and the arbitrary Lagrangian Eulerian scheme. We validated the model against experiments. We placed different samples with different aspect ratios in an anechoic box that we built in our laboratory. We measured the sound pressure level and compared it with model predictions. In general, the model captures well the natural frequencies of the different modes and the quantitative and qualitative trends of the sound pressure level. Then we used the validated model to evaluate the dependency of the speaker response on a set of design parameters so as to provide general guidelines for design. For the aim of this analysis, we analyzed the speaker response in terms of the sound pressure level frequency response and the eigenfrequency of the first structural mode corresponding to a bubble-like transversal vibration of the membrane, which in practice gives the cut-in frequency for the acoustic response. We first evaluated the effect of changing the membrane thickness while leaving the electric field unchanged. The sound pressure level increases by increasing the thickness until it reaches saturation. When the thickness is relatively small, the acoustic pressure on the membrane is quite large compared to the inertial loads, and it limits the vibration speed that the membrane can achieve. When the thickness becomes large enough, though, the dynamic is entirely governed by the elastic, electrostatic, and inertial forces on the membrane, all proportional to the thickness, while acoustic loads become negligible. This can also be seen in terms of the eigenfrequency of the first peak. For small thicknesses, the acoustic added mass has a large impact, and it causes a reduction in natural frequency compared to the case in which the membrane has a large thickness and hence large mass. In this latter case, the acoustic added mass is negligible compared to the membrane mass, and the natural frequency is close to the value that would be measured in vacuum when no air pressure load is present. In practice, increasing the thickness above a certain threshold does not provide any advantage in terms of the speaker acoustic response. We then evaluate the effect of changing the diameter of the membrane while leaving the aspect ratio unchanged. Increasing the diameter leads to an increase in the maximum sound pressure level because the radiating surface increases, but it also causes the frequency response to shift towards the bass range. That is similar to conventional speakers. The choice of the radial dimensions has an impact on the range of the driver. This is reflected by the eigenfrequency of the first structural mode. Again, whereas in a membrane vibrating in vacuum, the eigenfrequency would decrease with the inverse of the diameter, the actual trend is different because of the contribution of sound pressure loads, which is especially important for large diameter speakers. In conclusion, we are working on coil-free loudspeakers made of dielectric elastomer. We studied a layout called conical dielectric elastomer loudspeaker, which consists in an initially flat annular membrane deformed out of plane between two rigid frames. The membrane can produce sound as a result of the structural vibrations induced by electrostatic forces when a voltage is applied on the electrodes. Here we presented a multi-physics model of the system, and based on that, we investigated the influence of a set of design parameters on the acoustic response. Thanks for the attention. Feel free to contact me if you have any questions.